All right, hey everyone, go ahead and get started. So I'm going to start with a example of some buoyant force, and then we will go into a little review of what's going to be on the quiz on Tuesday. And then I'm going to it's going to be like a general shorter class than normal. So I'm going to pass back the exams, and I'm also going to explain how this extra credit thing's going to go. And so we're only really doing something new right at the very beginning. All right, so this is when we were talking about buoyant forces and about things that float versus don't float. Say we're given a problem and it starts out like this. It's easy to find the forces. We've been doing this for a while now. So let's find the force of tension in a string that's holding a cube that's, something with this dimension. So we have, we have a cube that is hanging from a string, and we want to figure out the tension in the string. So that is, tension is going upwards, tension, and we know that that's just hanging from there. We know that it's going to want to be forced downward. That's the weight of the object, downward. All right. So pretty much we're given the mass immediately, so we can find this. We can say that the force of gravity, or the weight of this object in air, is equal to 10 kilograms times 9.8 meters per second squared. I made this an easy example. We have a force going downward of 98 newtons. So that's this object's weight while it's in air. And the problem stops there. It doesn't, describe it moving at any point. So I'm assuming this is something that is just hanging there. So that means that if I sum all of the vertical forces, it comes back to this thing, this whole same dance. We have a positive force going up. So we do all the positive ones first. And then we subtract the negative ones that are pointing down. And that is equal to however this mass is accelerating in the y direction. Since I said earlier, it's not moving up or down, it's not accelerating up or down, that whole side goes to 0. And this is our little proof. When we get down to here, we can say that tension in the string is equal to the weight of the object. Pretty much that's how we show definitively what the tension is in the string. And in this case, it's 98 newtons. While in air. In air. All right, we'll add a little bonus question on top of this. What's the density of this object? So, trying to recall what the density equation was. That was the one with the fancy looking Greek letter, like that. That's called rho. So it looks like a fancy P. That's density equals something over something. Mass over volume. Mass over volume. If you ever get confused on This is what I've tried to do when I've had some really nasty equations with a lot of variables in it. I would call this a capital V for volume, and if you need to make it look different, I would go like this or something. I don't know. Just so you know that that's volume and not velocity. It's different. So the density of this object is 10 kilograms over 0.08 cubic meters. And someone with a calculator, let's shop that out. Let's see. Should equal what I have. Just want to make sure.
1,250.
Yes, awesome. 1,250, and if we don't know the units, we can just use the units that we have already. So I have kilograms over cubic meters. So I can say kilograms over cubic meters. And those units are correct because I'm keeping it consistent. All right, so we have the tension in air and we have the density of the object. I'm going to actually put this up on the board so I remember it. I don't have that much room. I write too big. So the tension in air is 98 newtons. The density of, we're going to say, of the cube. Kilograms per cubic meter. There we go. So I'm just going to save those for later. So they're going to help me for the next part. All right, so we've found the tension in air. What if we take that same system, we take that block, and we submerge it in water? Or it could be any other type of fluid. They'd give you the density. I'm giving you the density of water in this problem right here. So we take that cube, it's attached to the string, and we're going to find out that the tension is not going to be the same. There's this buoyant force. The water is trying to push the cube upward out of the water. So let me, where do I want to put the picture? I'll put it right here. All right, so I've submerged the cube completely in water, and it's the same sort of thing where I look at the forces that are in the system. There are the same as before. There is a, let's bring up the red, there is the weight of the object. The weight of the object, which is mass times acceleration, m times g. And there's the tension in the string, that's still there. But there's one more thing. So we're submerging this thing in a fluid. And there's this new force, this new upward force. It's called the buoyant force. I think your book calls it just capital B. I don't like that. I like, telling you that things are forces. So that's force, or buoyant force, or normal force, or force of gravity. So I always say force buoyancy, or force due to gravity, things like that. Okay. So
So, Professor?
Yeah.
So, there are two forces going in the up?
Yep.
Okay.
Yes.
And which one's larger?
Which one's larger? We're going to find out.
Okay.
So, this question is asking, what is the tension in the string now that we've submerged it? So we can sum the forces again. Let's sum the forces. Let's figure out what we need to do. So I'm going to sum the forces in the y direction, in the vertical direction. And now I'm going to list all of the forces. So everything that's pointing upward is positive. Start out with tension, that's pointing up, positive. Now there's another one, also pointing upwards, the buoyant force. So plus the buoyant force. And there's nothing else pointing up. So that's all the positive values. Now we need to add the force pointing down. Those are negative. Minus the weight of the object, or the force of gravity on the object. And those are all of the forces in the system. So we can end this little sentence here. We can say is equal to the mass of the object times how it's accelerating in the vertical direction. Again, the question doesn't say I'm like accelerating it out or I'm like lowering it in still. So we can assume that this is at rest, which means that this term right here is 0. It's not accelerating up or down. All right. So finding tension is turned into something fairly easy. That's the equation we have. We just have to get tension on one side of the equal sign. That's pretty much it. So we have tension is equal to the weight of the object minus the buoyant force. Well, what is the weight of the object? What is F sub g that I have right there? I should have written that one down too. So that one was that's the weight of the object in air was 98. Nope, sorry. No, it was. Yeah, it was. Because it's equal to the tension. Thought I was going crazy. Okay. So we have the weight of the object in air. We have F sub g. So that's 98. But what is the buoyant force? What is F sub b? What is this right here? We don't know that yet. Then we need to go back and see how do we actually calculate this buoyant force. What does a buoyant force mean? Buoyant force, B-U-O. The buoyant force is equal to the weight of the displaced fluid. I think that's how I phrased it. So it's equal to the weight, GHT, of displaced fluid. Okay, so how do we do that? Well, what is weight? Weight was just that force. This is the weight. This is the weight of the object in air. And that's mass times acceleration. So we say the buoyant force is the mass of the displaced fluid times gravity, right? So we can say, well, maybe we use the mass of the water it's displacing. So I don't have a cube. Imagine I have this. It's displacing a certain amount of water. It's equal to its own volume. The water rose up a certain amount. That amount is equal to the volume of this example sphere. So we have maybe a volume, but we don't have the mass of the water. So we can use density. So I do give you the density of water right up there. Not used density. Whoop. Well, that's no good. Okay. We'll go like this. I'll start from right here. F of G minus F of B. We have B is equal to displaced fluid. So density was mass over volume. So that means I can find the, let's see, so makes it a little tougher. The density of water, and the other one was density of water. 1,000 kilograms per cubic meter. So that means I can use that density that they already gave me. I know that the cube is going to displace its own volume of water. So we have that jar. So if I put an object in the water is going to be displaced by however much material is in it. So we have that volume. That means we can solve for the buoyant force by using this as the mass term. I think I jumped straight to this in the formula I gave you guys. Displaced fluid. Displaced fluid. I don't have enough space. So let me summarize that. Let me, instead of writing that all out, I'm going to say the buoyant force is now equal to the density of the displaced fluid times the volume of how much fluid was displaced times gravity, acceleration of gravity. All right. And from the, let's see, on these slides, I can't go back to previous slides. We had a volume of 0.008 cubic meters. That was for the cube. So that means when I put the cube in the water, it's going to displace that much fluid. So then we have 1,000 kilograms per cubic meter times 0.008 cubic meters times 9.8 meters per second squared. We have a buoyant force of, let's see, what did oh yeah, that is that. So we have 78.4 newtons. Previously, I said we had, let me just finish this out with tension is equal to, what was it? We have the weight of the object in air, 98 newtons. Then we have to subtract the buoyant force, 78.4 newtons. So after doing this, after lowering this object in the water is sort of pushing up. It's sort of helping lift this cube. That means there's less tension in the string. We have a total tension of 19.6 newtons while submerged, or I could say in water. Okay, so this sort of little trick right in here, instead of using the mass, maybe they don't give us the mass. Maybe they don't, so you look up here, they don't give us the mass in this problem. Instead, I use what they do give me, the density, right here, and a volume that I already know, in order to solve for that mass, in which I use to make the rest of the problem easier. All right. So with this, I was going to use, let's see, I think I have one more slide after this. Okay. I was going to do a little conceptual thing. We have a tank of water, and let's say I'll draw a quick picture so I don't have to come back over here for a minute. So we have a tank of water. Let's go this. And I don't know, I put a car in it. Something really huge and heavy, like a car. I let it sink. Up, up, up. There's a car. Okay. Car's going to be pushing a lot of water out of the way. And let's say I throw a ping pong ball right next to it. Ping pong ball is going to float. It's going to be up here. It's going to kind of be, submerged a little bit, but it's going to be floating. Now, in this little diagram, so Fresno State physics department, the budget won't let me sink a car for you guys. So I have this. That's that. I can't afford a ping pong ball. So there's that. Now, which of these two objects has a greater buoyant force? So let me write this. Which the car or the ping pong ball? Who says the car? Raise your hand. Who says the ping pong ball? Raise your hand. Let's go through. We'll have, if anyone wants to try to explain your side, why the ping pong ball? For someone who's chosen that. Okay. You might think, it's because this thing's floating. And, all right, it's floating. That means it's, a lot of force upward. Sure. But remember what buoyant force was the mass of displaced fluid. So the weight of the displaced fluid, I should say. And so the car, I don't have a car, imagine a whole huge car in the water, and imagine how much water it's pushing out of the way. All right, so that's an amount of water bigger than this table. So that's the displaced fluid. Find the mass of that, multiplied by gravity. That's the buoyant force pointing upward on the car. So there's a huge buoyant force on the car. The thing is, the car is more massive. It has more force downward with its own weight. The weight of the car makes it sink. When we look at this ping pong ball, I drop it in, it just like barely pushes any water out of the way. It's not displacing really anything. It is displacing some. So the mass is small, very, very small. It's only pushing a little bit. So it's a very small buoyant force. But the thing is, the mass of the ping pong ball itself, the weight of this thing, is small enough so that this buoyant force is bigger. So I'm going to try to show with arrows. So that's even too big. So the buoyant force is large enough to let the ping pong ball float upwards, and it will displace an equal amount of an equal weight of fluid of its own weight. All right. So it's our little conceptual brain teaser. What else did I want to do?
Professor?
Yeah.
How's the fluid being displaced? Like, what do you mean by that?
Displaced, just pushed out of the way. So you get into the bathtub, you see the bathtub water rise. Because originally it was just water, and now it's water and you. Your body is physically pushing water out of the way. Or this thing, this car, you watch the water rise, has to push water out of the way for this thing to exist in that same space. Right? Does that kind of make sense?
But the mass never changes, correct?
The mass of this object does not change, but it's displacing a certain mass of water. So it had to push that much water out of the way.
Okay.
That's what I'm trying to say with the mass of the displaced fluid.
So the only way to calculate that is through density, right?
It's usually through density, yeah.
Okay.
And so I think that is about it. We'll go through a little. Okay, that's that. We'll go through a little bit on rotation. I think I have one more. Maybe. Okay, awesome. So for our quiz, we're just doing things on rotation, nothing on fluids. I just finished fluids. So what does that mean? That means rotational motion. Let me write this down. Rotational motion. So remember the old final minus initial, just what kind of angle does a spinning thing sweep through. Going over, this is, similar to position, whereas this next one, delta omega, is similar to, or I should say, let me not do delta. Let me just do omega average is equal to the change in angular position or angular displacement over change in time. So that's similar to velocity, almost identical in all of the equations we use. Then we had same type of thing for acceleration. This is angular acceleration. Let me try to make that better. So this is alpha. Looks like a fish. If it's so similar, we should know that it is the change in velocity, angular velocity, over the change of time. All right, there was that. Going from these rotational coordinates into the tangential components. So there was like V is equal to R omega and A is R alpha, where R is the distance away from your pivot point, whatever you're spinning. Maybe we have an arm that throws a ball. We can figure out how fast the ball is going to go. Right when we let it go, it's going to move in a tangential velocity. Okay, so there was that. What else? Yeah.
So Professor, this is tangential velocity and tangential acceleration?
Yeah, so those are just like a regular velocity that we're used to.
Oh, okay.
In the first chunk of the semester.
Okay.
So that whenever I say tangential, that's just linear velocity.
Okay.
Things that move in line.
Okay.
And linear acceleration.
And R, can that also stand for like the radius?
That's the radius. So if I'm swinging a ball around, it's the radius from the pivot point to wherever the ball is. Or if I have a wheel that's spinning, that's the radius of the wheel.
Okay.
Yeah. Okay, so there's that. We had I should say rotational kinematic equations. So these are for something with a constant angular acceleration. Constant angular acceleration. So they look identical to the ones we are familiar with. I'll do 3 of them at least. So that's one of them. We have we have a angular displacement is equal to the initial angular velocity times time plus 1/2 angular acceleration times time squared. Okay? So like flooding back your memories of homework and using these. Yeah.
I apologize for all these questions.
No, it's fine.
Is that a theta? Like displacement, is that theta or?
Yeah, so that is theta. So that's what I've been doing for most of them. For all of these right here, those are theta.
Okay.
So that's just the angle that this rotating thing sweeps through.
Okay.
Okay, so that was chapter 7. I think it was all of this stuff. I think chapter 8 was there's only torque. So we had torque, which was this lowercase tau, fancy looking t. R cross F, R, F, sine theta. So this is a cross product on that top one, which means the second line, cross F. Okay, so remember, torque was something where you can have the same amount of force, but by increasing that radius, we get something that is a bigger twisting force. Remember, torque was a turning force, or twisting force, turning force. It's torque, and that's a force. Next up was, I think we went right into angular momentum right after that. No, we went to moment of inertia first. Moment of inertia, that was me looking at the mass and how is it oriented on something that's spinning. Is the mass really far out or is the mass really close in? That was with me spinning on that stool. That's connected to angular momentum. I'll get to that in a minute. But if something is really far out, from the pivot point, say my body is the pivot point, it was hard to start to rotate. Those are the guys with the dumbbells. They were trying to spin them back and forth. When the mass was far away from the pivot point, we had a greater moment of inertia. Remember, moment of inertia was capital I, what was it? It was mr squared. And I said if I give you some really crazy shape, I would give you like a little moment of inertia. You don't have to solve it. But if it's a very simple shape, maybe you would have to solve it. And I did a couple examples of some relatively simple shapes. Okay. Then the moment of inertia led into angular momentum. That's what I was doing that day. There we go. And this had a couple forms. I said it was R cross P. And then I showed you guys how it was equal to I omega. Let's see. Yeah. Center of mass?
Yeah.
Center of mass was in there, yeah. So we had it right, kind of like right here. It's good to mention it right now because maybe you'll remember later, and then I forgot to tell you guys about it. So, okay, so right here, we had like center of mass of something. What was that? That was M x 1 plus M 2 x2, and so on. There we go. So that was like just a horizontal center mass. And then I found a separate vertical center mass. And then I just related to where the two intersect one another. I did that on the board. Yeah.
In our homework, it talked about the z-axis, but we never really talked about that. And then it also talked about transversal speed and how it's related to rotational kinetic energy.
Yes. So I did do rotational kinetic energy. I think like one slide on it.
But can you tell us like the relationship between that and transversal? Because aren't they inversely related?
So I'm gonna like put this over here. I think I had a little thing where I said rotational kinetic, rotational energy, and then I started out by saying like was the sum of many. Oh no, this was sorry. Rotational kinetic energy. Was just regular kinetic energy like that. In the slide I did like a big long thing like that. And then I eventually got to, what was it? It was 1/2 I omega squared. So that's rotational kinetic energy. Okay. Yeah. So I would say, remember about like all the quizzes we've had so far. We've had 2. I didn't make it like super long. Hopefully you'll get through it in like, well, I'm planning on having you guys get through it like half of a class length. So it's only be a handful of questions. Try to pick out which homework problems I like focused on, you guys practicing, when you review this stuff. Okay.
Professor, one more question.
Yeah.
So for the moment of inertia formula that you gave us, for what shapes would that refer to?
So that's a very general one. That's if I give you just like a point mass here and a point mass here. And they're connected on a massless rod that connects the two. Yeah.
Just to clarify, those are the homeworks from chapters 7 and 8, right?
I think so, yes.
So a massless rod is actually a cylinder, right? And cylinder has a specific formula for its moment of inertia.
Right, so if we have like a, this is way too huge actually, just a point mass, something that is really tiny and it has some mass, like a little particle, a little atom. And I say, look at that one and look at that one over there. I call that mass 1, mass 2, and then I give you the problem. I say these two are actually connected, but the thing that's connecting them is massless. So imagine something that doesn't have a mass. So it's a physically impossible thing. And eventually we'll see, like, if you are interested, this is related, like, atoms and how they react to one another. But for this type of massless rod, the problem I always say, it's just this you can think of it as like a coat wire type of thing. You don't consider the mass of that at all. I'm only looking at that and that. When we do get to big sort of defined shapes, like an actual cylinder, you're right. So we have a cylinder. And then I say I'm going to rotate it around one end, or maybe around the middle. Around the middle. Then I will give you, if this is something like this, I'll give you a actual moment of inertia of that thing. You wouldn't have to solve for that. And then actually do the problem. So if there's something like a big shape, maybe it's a hollow cylinder, maybe it's a ring, maybe it's a cube. I'll give you that moment of inertia, and you wouldn't have to solve for it. You could just start from having that as your value. All right.
Will
Yeah.
you be giving, what formulas will you be providing us on this quiz if you are giving it?
So my quizzes, I will provide you the formulas that you will need. You could probably expect all of these to be up and available. I'll put them on the board so you could use them. It's just a thing of always knowing where and when to use them, making sure you are familiar with how to use these equations. All right, so I think that's it for today. I'm going to ask that, I'm going to do this a little differently. I'm going to hand out the exams, and I'm going to do it in like alphabetical order, and then afterwards, I will go over, no, actually I'll do this right now. So that way some people can leave if they want. That's extra credit, page right here. You have until November 16th to do your work, staple it to this paper, and turn it in. You can turn it in early if you want. It's up to you. It's worth 15 points. All of those points will go onto your exam score. So maybe you're thinking, maybe I get above 100. That's no. So 15 points, and these are actually pretty much the same questions that are in your exam. I'm just giving you guys more time to work on them. I added a couple more parts to some of the easier ones. So if you got a lot of the questions correct in the back half of the exam, then this is going to be real straightforward kind of points for you. If you didn't get full credit on the last half of the exam, on the written parts, then it is, you're going to have to work through it. And I do want to see you guys' work for these. I don't want to just have answers. I want to see each step. All right, so I'm going to say, I'm passing out exams. I'm going to say A through, so last name A through C. You come on up, and I will hand these back.